In this video, I'm going to discuss about the mathematics behind the generalized linear model or the GLM. In the traditional models, the model takes the form like this: yi is um, xi beta plus the epsilon, where epsilon is the error term. Xi is the matrix of all the covariates or independent variables, whereas beta is the matrix of all the parameters, the slope and the intercept parameters in the matrix form. Now the assumption here is that the error term is normally distributed with mean 0 and variance of 1 in most of the times. Well, in this kind of a model, there are a number of problems. First thing is that the assumption of normality doesn't hold all the time. So sometimes we'll have measured observations. So that could be count, that could be a quantity variables. So which may not follow non-normality. So assumption of normality is unrealistic many times. The second problem that usually is encountered is that we may not be able to, we cannot use the response variable which takes values within a range. For example, while modeling probability, probability has to be always between 0 and 1. So that's the restriction, the upper bound and the lower bound. The problem is that the covariate can take any value. It can take values from minus infinity to plus infinity. So you cannot use this kind of a model to model for probability of something. So if the response variable or the intention is to model for probability, you cannot use the traditional linear models, which has a range between minus infinity to plus infinity for the covariate multiplied to the estimates value, which is the expected value of y. In GLM, and yeah, the last problem is the constant variance. Uh, well, this is an assumption also, but this is unrealistic. So the variance of data usually is not constant all the time. So because of these three problems, sometimes traditional models don't perform well, or there tend to be some sort of a biasness. So GLM comes as a rescue. Um, the mathematical form it takes is that the expectation of y is a function of g, um, and the g is the link function. So it takes this kind of a form. The well, the expectations is similar to the traditional model, except the fact that we have a link function here, which relates the average values or the expected value to the y values or the response variable. So and that is sometimes or most of the times non-linear in nature. And g belong to the class of probability functions known as the exponential class of probability functions. Now you may need to go through what are the exponential class of probability functions. For more details you can search in web. So and this is estimated using the GEE estimation. Now after doing the estimation, um, we can also find out the standard error, confidence interval, and we can do the hypothesis testing pretty much the same way that we do uh, uh, for traditional models. So there is hardly any change for estimating the standard error, confidence level, or doing the hypothesis. In this video, I am going to discuss about what are generalized linear mixed models. The generalized linear mixed models are the models used when we assume that there is random effect in our data set. So one of the assumptions is that there should be random effects. So random effects are nothing but this subject specific effect on the data set. So if there are couple of subjects, say for example there are three products, and we are analyzing the customer preference for three products. There could be some of the effect which will be totally dependent on different products, totally random. So there is a difference than the population average. It's total, the effect is totally different than the population average. So that is known as the random effect, and the population average is known as the fixed effect. So the assumption is that there is a presence of a random effect in the data. So this model deals with the correlation and non-constant variability very well. So whenever we have observations which are correlated, and the observations are having non-constant variance, then these models are also very useful. We can also use this when the distribution is of exponential type. So the data has to be distributed exponentially. So some of the exponential distributions are binary, uh, Poisson, normal, beta, and gamma distributions. If there is no random effect, then it's same as the generalized linear model that we have seen in other videos. So if there is absolutely no random effect, it's exactly same as generalized linear models. So where can we use it? We can use these models where the observations are repeated measurement of the same experiment for different subjects. So in that case, since the observations are repeated measurement, so there is a high chances that the observations will be correlated observations. So in this case, we can use generalized linear mixed models, and there is some random effect in the data. So that could be due to the subject specific regions or totally unknown regions. One of the example that we can give is if you want to analyze the customer preference between product A, B, and C. So one other thing is that we can do an experiment and do and collect data. So that could be that could be highly correlated data because the same product is being used for experimentation purpose for a number of times. So the data will be correlated, and there will be random effect as well, because there will be subject specific effect. There are three subjects here, three different products. So the customer satisfactions or customer preference could be totally because of some specific characteristics of the products. So that could have some specific effect known as the random effect. So in this kind of an example, we can go in for the generalized linear mixed models. In a separate video, I'll discuss about how to build such a model, and I'll take an example and do it.